The example discussed in this video includes looking for the stationing and elevation of points in the symmetrical curve. Learn how they are solved here in engineering surveys. The problem involves a summit parabolic vertical curve with back tangent of positive 6 and forward tangent of negative 4%. The point of intersection lies at elevation 202 meters and station 35 plus 180. The curve should also pass through a specified point W with elevation of 198.13 meters and station 35 plus 160. We are tasked to determine the length of the curve, the stationing, and the elevation of both PVC and also PVT. Let's illustrate the curve first. A back tangent of positive 6% intersects a forward tangent of negative 4%. The point of intersection is also elevated at 202 meters in station 35 plus 180. Besides this point, another is also specified at elevation 198.13 and station 35 plus 160. This point is labeled W. The first one to tackle is the length of the curve. From the illustration which was drawn, we can also generate some data, such as labeling the distance from PVC to PVI as half of L, as we are dealing with a symmetrical curve. From the stationing of PVI and point W, we can also deduce that point W is half of L minus 20 from PVC. Next, let's lay out all the functions for the elements we derived in the previous video. There are equations for A and B. There are also functions with S1 and S2. Then, there is an equation for H, and also x squared upon y. The functions for A and B cannot be used this time, as they are actually the latter tasks B and C. The functions for S1 and S2 are also irrelevant, as we are not to look for the highest point on the curve. Now we are left with the last two functions, and checking upon them both, there is L in them. Since we are looking for L, we cannot use the first function as we have no H. For the next function, we have no clue about X, Y, H, and L. So in order to minimize the unknowns, let us plug in H into the last equation to make it as a function of L. X squared upon y is then L squared over 4 of H, which is now an 8 of L, with G1 minus G2. Cancel out L's and reduce the numbers to get X squared over y as equal to L upon half of G1 minus G2. Now place 2 up to the numerator and get X squared over y as 2L over the difference of G1 and G2. This is the simplified function we can use. All we needed to do now is to clearly define what is y, as the g's are already given, and from the illustration, we can see that x is half of L less 20. So let us solve for y. Y is the offset from the tangent to the curve aligned with point W. Start by working on a small triangle on PVI. Gradient is rise upon run. The grade is 6%, which is 0.06, equated to the height over 20. By cross multiplication, the height turns to be 1.2. That is the vertical distance from PVI to point Q. Point Q is the intersection of the aligned point W to the tangent. Now using the elevations, Starting from PVI, which is 202 meters, deduct the height taken from the gradient, which is 1.2. The elevation of Q is then 200.80. This is just a little above point W, and since we are looking for their gap, we again subtract the elevation of W, that is 198.13, giving Y as 2.67 meters. With Y already known, get back to the proportionality and plug in the known parameters. There is the square of half of L less 20 upon 2.67, the value of Y. This is equated to 2L upon the difference of the grades 0.06 and negative 0.04. Cross multiply and expand the square to have 0.1 of the trinomial, a quarter of L squared minus 20L plus 400, which is equated to 5.34L. Distribute 0.1 and get 0.025L squared minus 2L plus 40, which is equal to 5.34L. By using quadratic equation, we can find the value of L as 288.0453 meters. With task A already completed, let's figure out the stationing and the elevation of the point of curve. Since we already determined the length of the curve, we take the station of PVI, which is 35 plus 180. Then subtract L over 2, which we computed as 144.0227. The result is the station of PVC, which is 35 plus 035.9773. For the elevation, we use the gradient. The back tangent has a grade of 0.06. This is height 1 over the length of 144.0227. Height 1 is then solved as 8.6414. So take the known elevation of PVI, which is 202 meters, and since PVC is lower, subtract height 1 and get the elevation of PVC as 193.3586 meters. The computation for the location of PVT is also similar. For stationing, take PVI at 35 plus 180, then add half of the curve's length, which is 144.0227 meters, to get the station of PVT as 35 plus 324.0227. Then for its elevation, compute for the vertical distance of the 2 points from the grade. Height 2 is 10, the grade of 0.04 multiplied by L over 2, which is 144.0227. Height 2 is 5.7609. To convert this into elevation, start from PVI of 202 meters, then subtract height 2 of 5.7609 to get the elevation of PVT as 126.2391 meters.